We have indistinct things and we can keep using them, but we're only going to do 4 steps. It's going to be n to the r. Perfect. So that leaves us with this one. But before we do this one, I want to actually do a different question. Hold on. I want to do a different question before we, well, actually, before we do that, and before we do that question, we've decided that n choose r, or we constructed from what we knew about permutations. So it first was a permutation of n things taken r at a time, and then we divided out all the permutations of each group of size r, right? And so that's our formula that we now know for all times. Now, a useful identity, which you can show algebraically, but I want you to give me an argument, like a combinatorial argument, is that n choose r is equal to n choose n minus r. So you can easily show this algebraically, right? N choose r is n factorial over n minus r factorial r factorial. That's what n choose r is. N choose n minus r is n factorial over n minus r, I'm sorry, wrong thing, over n minus r factorial, n minus r factorial. And if you simplify this, this just becomes r factorial. So they are, in fact, equal. We can show it algebraically, but I want you to give me an argument intuitively. Does anybody feel like they can do that?
I know that there's a, like, you can use a Pascal triangle, and then like they're kind of always on the opposite sides of each other. Not opposite sides, but like they're kind of corresponding to each other in a way. I don't know how to explain it exactly, but
Now
it's like if you have r on one side, and n minus r has to kind of be on the corresponding other side of it.
Okay, let's think of it this way. Let's say I want to choose from these 10 people a group of size 3. What am I not choosing? Or what am I also choosing?
You're choosing 3 to include, but you're also choosing 7 to exclude.
Yes.
And they're the same number.
Yes. So every time I choose 3, I'm also choosing the rest, right? It's like the 3 that I want and then the rest that I don't want. So for every group of 3, there's going to be a group of the total number minus 3, right? So it's like the chosen and the unchosen. I think that's what you were trying to say, Jalen, on the opposite sides of, right?
Yeah.
Yes. Perfect. That's a good thing to be able to understand why this is true. And this, it's easier to see. Like if I said 5 choose 2, that's going to be equal to 5 choose 3, right? And we can easily see that algebraically. Those add up, right? So it's 5 minus 2, 2 factorial, and this is 5 factorial over 5 minus 3 factorial, 3 factorial. And we can easily see that that is the same algebraically, but even better, if I choose 2 from the 5, I'm also not choosing 3. So that's a choice in itself. Excellent. Okay, let's do, before we move on to the stars and bars, let us work this problem. Hold on, it's not syncing. Okay. So when you're facing a counting problem, you always want to ask yourself, does the order matter? What's what? Okay, so we have a group of 8 women and 6 men. So what I want you to start thinking about in terms of these problems are the things that are distinct and the things that are, okay, so let's come back over here for a second to these 4 problems. There they are. When I say indistinct objects, those are going to be true in every one of these 4, oops. In every one of these 4 problems, we're going to have distinct objects, be it letters or people or bins or bagels. They're going to be distinct objects. And then we're going to take a group of those objects, and those objects are either going to be distinguishable, or they're going to be distinguishable or they're not. And I'm going to care about their order or I'm not. I'm sorry, now that's the distinguishable or not. I'm going to be able to repeat them or not. Okay, so those are the things. So if you think about an urn, those are your distinct objects. And then balls, ordered or not ordered, repeat or not repeat. Okay? What? You just made it worse, but I promise it'll all nice come together. Okay, so here, from a group of 8 women and 6 men, a committee consisting of 3 men and 3 women is to be formed. So if I just asked you how many committees of this form would be, so don't even look at A through C. Well, remember when we talked about steps versus choices. So our first step might be to choose the women. And so my women are distinct objects, right? Those are the urns, if you will. The balls are 3. There are 3 of them. Okay? And I'm going to go grab those 3, if you want to think about that. And do I care about the order of these balls? No, this is a committee, so I don't care, right? It's not like I'm making a president, a vice president, a treasurer. I'm just going to have 3 women on that committee. All right? And I can't repeat them, right? Once I use up a woman, I gotta grab the others from the rest. So what does that describe? Order doesn't matter, repetition not allowed. Anybody? Choice, good. And yes, that's going to be a combination. So of the women, we're going to choose 3. All right, then our next step, if this is just, we're having no restrictions. So second step, let's do a step. Second step is that was choose the women. We're going to choose the men. And since this is a step, we're going to multiply, right? This and then that. And this time it's going to be the same, 6 choose 3. Easy, that's total possible committees of 3 and 3. Okay, but if I then wanted to look at A, 2 of the men out of this 6, let's say Justin and Jalen, they're at the top of my box, they refuse to serve on the committee together. Okay? Now we can count this in probably several ways, but 2 common ways. One way is directly. Okay, so we still have our first step. We're going to choose our women. No restrictions on them, right? So that is 8 choose 3. But now I have a choice to make on the next step. So one of 2 things can happen. What are they? Justin and Jalen will not serve on the same committee. So either, really, you can think of it as 3 things happening.
I feel like since it's me, I should answer. Either one of us is in a group, either of us are in a group, or in the case where like we both are, like just don't count it.
Okay, so of the cases that we're allowed to use, what you just said, one of you is in there. Well, one of the men from that group is there, just exactly one, and the other is neither, right? Those are the 2 things that can happen and satisfy A. So how do I count if one of you is there? Well, first, which one? Do you have a choice? How many ways can one of you all serve of Justin and Jalen? 2. All right, so one of those is going to be there. So it could be Justin or Jalen. Now, given either one, I then need to choose the remaining 2 men. Out of how many? 4, right? So there's Justin, Jalen. Let's write all the people down. Alan, Daniel. Let's see another one. Zark. I like that name. Zark and Uday, who's not officially in our class, but he is going to be on this committee maybe. So here are my 6 men. I pick one of those, Justin or Jalen. And then of the remaining non-Justin or Jalen's, I pick the other 2. So that's going to be 4, choose 2, right? Or, and since it's an or, it's a plus here. Neither of them serve. So how do I do that? Of the 4 that aren't Justin and Jalen, you're going to pick all 3. That makes sense? Now, that's if we do it directly. What's another way that you could count these? Maybe with slightly less steps. Case 1 was one of them serves, or neither. Anybody think of a faster way to count this? How about we take all the ways that we could do this? 8, choose 3, 6, choose 3, and subtract off. Yes. Subtract off the cases where they both serve. So we still have the 8, choose 3, because that's still what we got to do for the women. And then we subtract off. So if those 2 are serving, Justin and Jalen are on there, then really we only need 1 more from the remaining 4. Yeah? Speaks louder than your questions. Maybe it's so easy you're bored. Is there also a 2, choose 2 multiplied to the second term? Yeah, you could if you wanted to. I mean, that's not incorrect. So if you want to do that, that is just 1. So you could say of the 2, choose both of them. Then of the remaining 6, choose 3. There's nothing wrong with that, Ed. But you don't have to, because it is 1. Yeah. Cases. Because they're not coming from the same set, right? So she serves, he serves, neither serve, right? If she serves, then really of the 7, you choose 2, and then what? He's not serving, so of the 5, choose 3. If he serves and she doesn't, that means, let's count the she's. Of the 7, not her, choose 3. Of the 5, not him, choose the other 2 since he was already chosen. I'm going to look at you in a minute, Tommy. Or neither of them, which means of the 7, not her, choose all 3. And of the 5, not him, choose all 3. Let's see. 8,